Okay, this is senior math class, and this is Immaculate Conception Apostolic School. What day is today?
The 13th.
Oh, 13th, April 13th, 2015. Today you're going to be doing one of Isaac Newton's lemmas, that I hope we can get to today. Isaac Newton wrote the Principia, the mathematical principles of natural philosophy. We just call it Principia. And in the Principia, does anybody know, have anybody heard of the Principia? What are you doing in the Principia? Okay, that's not this class, but the point is, what Newton did in the Principia is he first introduced, this is where he introduces the mathematical lemmas to prove the properties of lemmas. But then he used those lemmas to discover the forces of nature, as he put it. We ended up with something called the universal law of gravitation. The universal law of gravitation, force varies directly with the product of masses and directly with the square root of distances. That's Newton's work in the Principia. That's book 1 and book 2. Book 3 does this really cool thing. In book 3, he takes the universal law of gravitation and he uses the universal law of gravitation to prove Kepler's laws. Have you ever anybody heard of Kepler? They have physics in it, right? Okay. But he uses the universal law of gravitation along with other principles to prove that planets should be moving in elliptical orbits with the sun at one of the foci, that the line from the planet to the sun sweeps out areas proportional to the time, and that the period zones is the ratio of the average distances to the sun. And it's really cool that he was able to prove that the planets behave that way. Okay? But are we going to do all that today? No. We're just going to do one lemma. One lemma. And we're going to do the lemma that introduces the derivative, the lemma that we use to understand and give a geometric understanding of the derivative. That's our work today. And the derivative, if you remember, is the tool that we use to discover the slope functions for continuous curves. The slope function for continuous curves. Now there's a new word there that we haven't used before, and that's continuous curve. In order to understand the lemma, we have to understand what a continuous curve is. And in order to understand what a continuous curve is, we look at our work with tangents already. The tangents that we've worked with, last year Euclid, right? With Euclid, we proved that if I have a circle and I draw a line at right angles to the diameter, if CD is at right angles to AB, making what? Angle, if ABC is a right angle. What did Euclid prove if ABC is a right angle? Speak nice and loud, like Mr. O'Hare is nice and loud. Anybody hear me? Okay, speak nice and loud. If ABC is a right angle, what did Euclid prove? Anybody? I want to see hands. Francis.
CD is a tangent.
I didn't hear you. I'm kind of
CD is a tangent.
There you go. CD is a tangent. It's tangent to the circle. So if this angle is right, then CD is going to be tangent. Then with Apollonius, you prove that if I take a point on the, what am I at, D, I'm going to go E. If I take point E on the parabola, we drop ordinate EF, determining abscissa FG. And if I produce the diameter, a length equal to the abscissa, G, where am I, H? So if FG is equal to GH, what did Apollonius prove? Oops, let's do this correctly. What did Apollonius prove about EF? Nice and loud there.
EH is a tangent?
Yeah, EH is going to be tangent. So EH is a tangent if what? FG is equal to GH. If the ordinate equals the diameter produced. When the ordinate's equal to the diameter produced, then EH is the abscissa. I'm sorry, the abscissa. And then for the ellipse and hyperbola, I'm only going to draw one picture here for the sake of time. Take a random point where I'm at H, K, drop an ordinate, KL, determining two abscissas, M and N, and if I produce the diameter out to P and P such that PM is to PN as ML is to LN, then what do we know about KP? Nice smile. That's tangent. Okay, so that's all old news. But the really interesting thing, the thing that's going to help us understand continuity is, what did Euclid prove about the space between the tangent and the circumference of the circle? What did Euclid prove about the space? I want to see more hands. What did Euclid prove about the space between the tangent, BD, and the circumference of the circle? Everybody remember that? Okay. Good.
You cannot stick a line between the tangent and the circumference of the circle.
Yeah, you can't stick a straight line, you have to say, right?
Straight.
Right? You can't stick a straight line in this space. You can't. This is kind of a wondrous thing. It should be a source of wonder. Because a line has no width, right? There's no width to that line. And Euclid proved that we can't stick a line in what? In the space between. You can't do what I did with that blue line. Okay? Okay? And what did Apollonius prove about the tangent over here, Tony?
He proved is you can stick any straight line between the tangent and the parabola.
Good! Very good, Tony. You can't stick a line in the space between the what? Tangent and the parabola. You can't do this. Can't do that. And Apollonius proved that. And likewise for the ellipse. You can't do this. That's impossible. We proved that it can't be done. I'm doing the impossible. No. You can't stick a line in the space between the tangent and the curve. Now I'm asking, who cares? Well, it's kind of a wondrous thing. Okay? But what would the consequence be? Say I could stick a line in the space. Like that. You could stick a line in here and a line in there. What difference would that make? If you could stick a line in the space between the tangent and the curve, what would that mean? What would it mean? Joseph.
And there can be infinite multitude of tangents.
Well, at least more than one, right? Nice and cool. What is it? So then what would happen?
There's no unique point of tangency?
Well, there's a point B right there. Good. Okay, so point B right here. Isn't that a unique point of tangency? But he said, what did Joseph say? What did Joseph say? Francis.
There would be more than one tangent on
Tangent where?
on one point.
At point B. At point B, there'd be more than one. In fact, what Joseph said would be what? Potentially what? What did you say, Joseph?
Infinite.
There'd be a potential. Give me an example. Here, I'll give you a marker. Give me an example of a few of those tangents that would be more than the three that are on the board. What other tangents would there be at point B? Go ahead. Up. Would there be more than? So we have three there now, right? Would there be other ones besides those at point B?
If that can happen, this can happen.
Keep going. What else?
That,
And
that,
uh-huh.
that,
Uh-huh.
that.
Get the idea, guys? If you can stick a line in the space between the tangent and the what? The curve. Then in fact, how many tangents are there at a given point?
Potentially infinite.
Potentially infinite, meaning as many as you want. But what did Euclid prove about the circle? What did Apollonius prove about the parabola, the ellipse, and the hyperbola? What did they prove about those things?
That's absurd.
That you can't. You can't do it. You can't do what I did on this board with the blue lines. The blue lines are impossible. And if the blue lines are impossible, what does that mean? If you can't do it, then what does that tell us about tangents? For at least the circle, the parabola, the ellipse, the hyperbola. What does that tell us about tangents? About these curves? Francis?
Yeah,
There's a unique tangent in each point.
Yeah, every point has a what? What does it tell us, Tony? Every point has what?
Every point have one tangent.
Has only one tangent. Right? Every point has only one tangent. What does it mean, Anselm?
That you cannot stick line between the tangent and the curve.
And if you can't do that, what does that mean for us as far as tangents go?
That there's only one tangent and at each point.
Every tangent, every point has only one tangent. Okay? Every point has only one tangent. The way we say, yeah. There's a unique tangent at every point. Right? And this is what continuity means. A curve is continuous if at every point there is only one tangent. A circle is continuous. Euclid proved that you can't stick a line in the space between the what, the tangent, and the circumference. So there's only one tangent at every point on the circumference. Apollonius proved it for the parabola, proved it for the ellipse, proved it for the hyperbola. But those are each different what? Those are just four different shapes, four different curves. We want a universal idea here. What's the universal idea for continuity? A curve is continuous if every point has a unique tangent. Now, I'm going to draw my favorite figure here. I'm a big football fan, right? Is that a continuous curve?
No.
Why? Go to the board. Show. Why isn't it? Take it to, I got blue, find red. Why isn't it continuous?
Because these points, you could put a lot more than one, just one tangent.
Yeah.
And at this point. And the curve is only continuous, so you have one tangent per point. But like right here, that's just one.
That's one. Good.
But then there's a whole bunch of them.
All right. I think we get the idea. So there are 2 points here. I'll call this point X and point Y, right? Point X and Y are not what? They're points of discontinuity. They are points of discontinuity because at point X you have many tangents. At point Y you have what? Many tangents. But if I leave X and Y out of it, as Caleb pointed out, if I leave out those 2 points that look like that, well, this curve is going to be what? Continuous at this point. It's continuous if what? There is a unique tangent at every point. So there's 2 things about tangents and curves. The first thing, for a continuous curve, there's a unique tangent at every point. And the second thing, for every tangent, the tangent meets the curve at only one point. So how is the curve related to the line? Well, the tangent and the curve have only one point in common. And if the curve is continuous, then there's only one tangent at every point. So the idea that I have to drive home, because Newton just takes this for granted. He thinks when you're doing the lemma, he's just going to say, well, this is a continuous curve. And when you hear, oh, this is a continuous curve, what should you think? Well, that means what? There's only one tangent at every point. That's what continuity means for Newton. You clear? So that's the concept of continuity that you need in order to do the lemma. Now, let's set up the problem here so that we can appreciate. There's no point in solving a problem if you don't know what the problem is. And so, let's make sure we understand the problem. Start with the green dot. Now, if I put 1 point on the board here, how many lines go through that point? How many lines can go through that point? David, how many?
Potentially infinite.
Potentially infinite. Wow, show me. Show me all of them. I want to see all the lines that go through that point.
There, and then there.
Is that all of them?
No.
No. How many can go through that point?
Potentially infinite.
Okay, a whole bunch of them, right? So if I have only 1 point, there's a potentially infinite multitude of lines that can go through that point. Now, here's the problem. What if I have 2 points? How many lines go through 2 points?
Only one.
Show me. Different color. Make sure it's, yeah, you got it. We're into color coordination. Oh, right? So if I have only 1 point, then 1 point provides an infinite multitude of lines. If you want to find a unique line among that infinite multitude, is that going to be an easy task? Say I want to find a unique line among a potentially infinite multitude. Is it going to be easy to find that unique line? No. But what if I have 2 points? Is it going to be easy to find a unique line that goes through both of them? You bet it is, isn't it? 1 point, infinite multitude of lines. Hard to find a unique line, isn't it? Get the point? Okay, but 2 lines, if you have 2 points, boom, there's a unique line. 2 points determine a unique line. 1 point doesn't determine a unique line. 1 point determines, in fact, because we're just stuck in white space here, right? In fact, lines in 3 space, you have lines going all over the place, don't you? Right? So this 1 point doesn't do anything for determining. Now, why is O'Hare talking about that? Because it's a good question, isn't it? Okay. If I have a continuous curve and I have a tangent, the tangent to a continuous curve shares how many points with the curve? How many points does a tangent have in common with the curve?
1.
Just 1 point. The tangent has only 1 point in common with the curve. Right? How many straight lines are there through that 1 point? How many straight lines are there?
1.
There's just one?
Oh.
There's just one straight line through that point? Then you weren't paying attention over here, right? 1 point. Well, I know you can't see the point anymore, right? I'll make it bigger. Right? What? How many lines go through 1 point? Joseph.
Potentially infinite.
Potentially infinite, right? Okay? So if I have just 1 point on a curve, and I want to find the unique tangent, is it going to be an easy thing to do? That's finding 1 line out of a potentially what? Infinite multitude of lines. Not an easy thing to do, is it? What kind of line has 2 points in common with the curve? What kind of line has 2 points in common with it? David?
A secant?
A secant. Secant from Latin meaning what?
Cut.
Cut. NT means what? Secant.
Cutting.
NT, you know? OST, Mustis, and NT, you know?
Oh, they.
They cut. Pretty original. Secant means what? They cut. Tangent means
They touch.
they touch. This English language is pretty profound. But anyway. But if I have a secant, look at that. The secant has 2 points in common with the continuous curve, doesn't it? The tangent has only 1. And the genius of Newton is that he uses the secant to figure out the what? The location of the tangent. Of course you know the genius. We haven't done it. Okay, but okay, the genius of Newton is, okay, there's 1 line here that we're trying to find. This is the tangent. See this? We want to find this tangent, which is 1 line among a potentially how many? Infinite. This is 1 line among a potential infinite. And what do we use to find that tangent? Well, a secant is unique. Between these 2 points, there's a secant. And this is where the genius comes in. What happens to the direction of the secant as, I'll call this point A and point B? I hold point B fixed. Now let's do a little imaginary motion here. I'm going to hold point B fixed, meaning don't let it go anywhere. And this is what the lemma is about. What's going to happen to the angle CBD if A moves towards B along the curve? What's going to happen?
It's going to get smaller.
It's going to, what's going to speak clearly and loudly. Don't use its. I don't want any pronouns.
CBD
CBD.
will get smaller and smaller and smaller until smaller than any amount.
Okay, so it's going to become smaller than any amount, isn't it? Right? And so the direction of BC is going to approach what direction? What direction? This direction is going to approach what direction? Francis,
The direction of BD.
what is BD?
Tangent.
Tangent. And so as A approaches B, the direction of the secant approaches the direction of the tangent. Now, that's an introductory idea. Now we read the enunciation for this lemma. Class together, let's read the enunciation for Newton's lemma. What do we get?
If through a point on a continuous curve.
Stop. So, here's a point on a continuous curve. What's the point? B. Okay. So, just when I say stop, just stop. So, through a point on a continuous curve.
A tangent and a secant are drawn.
Stop. So, tangent is what? BD. And the secant is what?
BAC.
BAC. It's drawn and produced. They like to be produced beyond. Okay? So through a given point, a tangent and a secant are drawn. Okay, read on.
At the second secant point.
What's the second, stop. What's the second secant point? A. So here's your first secant point. This is your second secant point. What's the second secant point, class?
A.
Okay. So what? Read on.
Approaches the point of tangency.
So what does that mean? As the second secant point approaches the point of tangency. What does that mean?
As point A approaches point B.
Yeah, it's point A approaches point B. What's Newton's claim? Read on.
The angle between the secant produced and the tangent diminishes and ultimately vanishes.
So the angle, again, the angle between what, class?
The secant.
Secant, which is
BC.
BC. BC is your secant, right, Tony?
Yes.
Okay, and what's the tangent?
BD.
BD is the tangent. What's the answer? What's the angle? Nice and loud and clear. What's the angle between the tangent and the secant?
Angle CBD.
Okay, and what's Newton's claim? What's he claiming? Joseph, haven't heard from you. What's the claim?
The angle between, well, as the second point of
No, we use particulars now. As what point?
point A
As point A what?
approaches B,
Uh-huh.
the angle between
What's the angle? Particulars.
CBD
CBD
diminishes.
diminishes. What does that word mean, diminishes? Louder than here.
Decreases.
Decreases. Guess what? I like simple language.
Gets smaller.
It gets smaller. Right? That's right. So angle CBD gets smaller. And what? What does it use?
And vanishes.
And ultimately vanishes. And now we'll have a discussion of that later after you guys do this thing, because ultimate vanishes. So the angle between the secant and the tangent CBD, as point A approaches point B, the angle CBD diminishes, gets smaller, and ultimately vanishes. This is what Newton's going to prove in our lemma. So at this point, what we do is we're going to get you guys into the groups, groups of 4, and we're going to have you go through this thing line by line. Go ahead, line into the groups.
QR is a continuous curve, tangent PT drawn through point P.
Yeah, so
Draw a line.
PQR.
Everybody understand that or no?
Tangent PT.
Tony, there.
PQV.
Draw a line TR, meaning the secant produced.
Draw a line TR, meaning the secant produced the curve at R. Task is to prove that it's Q
Our
approaches P
our
along the
task
curve.
is to prove that as Q
VPT
approaches B along the
Diminishes and
curve,
ultimately vanishes.
the angle VBT
Putting
diminishes
points
and
P,
ultimately vanishes.
R, and T fixed. Let Q approach
holding
P
points P, R,
along the curve while PQ
R, T.
produce always
Fixed.
meets line
Let
R,
Q
T
approach P along the curve,
at B.
while PQ
Assume
approach,
that
while
as
PQ
Q
approach
approaches
always meets line.
One sentence at a
R, T.
time, guys. Everybody, just keep moving through.
Produce. Assume that as Q approaches
Always
P,
meets line.
angle VPT does not vanish.
Everybody got the reductio? This is a reductio proof. So we're going to assume that the angle doesn't vanish.
Let VPT approach some positive angle
Assume that
SPT.
as Q approaches P, angle VPT does not vanish.
since
What does that mean?
Q ultimately coincides with P.
It's a reduction. Everybody get it? We're going to assume that the angle what?
PS must fall in the space between the tangent PT and the curve,
If it doesn't vanish, then what's going to happen? Therefore
making
what?
PS tangent to curve
Angle VPT
PQR.
approach some positive angle. Therefore, curve PQR
Okay, you get it? Tony?
must have more
So if
than
it doesn't
one
vanish,
tangent
then it's going to
point
approach what?
But this
Some
is
positive
impossible.
angle. What?
Curve PQR is continuous.
Okay?
Can only have one tangent at each point.
Since
Therefore, our assumption
Q
that angle
ultimately
VPT will not vanish must be
coincides
false.
with P. PC and
So what's the
PS
problem?
must fall in the space
Therefore,
between
continuous curve,
BT
and then
and
moving
curve
this point here,
PQR,
assuming that it doesn't disappear.
If it doesn't
making
disappear,
PC
Then as Q
tangents to
approach this
curve
angle.
PQR.
yes, okay, we assume that it approaches some angle, right?
Therefore, curve PQR must have
So what? Big deal.
one
What's
tangent
the,
at
what's the consequence of it approaching that small angle?
But this is impossible. For curve
What's the
PQR
consequence? What's the next step?
is continuous and you
Yes.
have only one tangent at each point.
Why? And that's what you have to figure out. Why must that be a tangent?
Angle VPT does not vanish.
Convince each other that it is.
Therefore, if from a point on continuous curve by tangents and the secant
Okay, that's the
are from
conclusion. What's the problem in this
P.
Like, what I don't get is that they say like,
what's
Why
the
is it-
second tangent?
why is
Yes.
Why
the
is
produced
PS
line
a
always
tangent?
meets?
That's what I want you to
Or
make sure
PQ
you
produced
understand.
always meets line
Why
T
must
of B?
PS be a tangent?
Doesn't that make it a good line?
Because
What?
When it says,
PS
coincides.
when it
fall in
says
the
PQ
space
produced
between the
always meets
Because
line
Q coincides with
T
B,
of
and
B. I don't get that.
convince each other. Why must that be a
I
tangent?
mean, it's a secant though. Secant produced.
Okay, so as you move it down, it's still,
PQR.
a secant still has to hit that B, so it's gonna be like,
Yeah.
oh, okay, okay.
And so there's only
Okay.
one
I mean,
point.
since Q
Yeah.
approaches P and the secant moves up, but it says the angle between this VPT will not vanish. That's what they are saying. So
Okay.
he said, well, gotta be SPT somehow like a positive angle there.
Okay.
But you see, we have two tangents, but
You
we
stack
gotta figure out
Why must
like
flux?
SP is a tangent.
Because like he was saying that the
Why
continuous
must
curve
PS be a tangent?
means that
Read-
there's only one
read
tangent
it
at
through
every
again.
point.
If you're not seeing it,
And so we
say
need to find
therefore,
that there's
at some
only one
point it
point for
says what?
PS, and
That-
since QP
That PS
is
a tangent.
ultimately approaching,
What makes us think
like
that
Q is
PS
ultimately
tangent?
coincides with P,
Is it that VPT does not vanish?
and therefore PS has only one point to the
Like,
to the
based on the
continuous
assumption
curve,
that Q approaches P,
and therefore it has to become a
so
tangent.
therefore, that
Because it's a continuous
approach
curve.
positive at SPT.
Yeah. PS
Right?
touches at one point, therefore it must be a tangent.
So they're
Yeah.
Why is it a tangent?
Because
Francis, go ahead.
Francis?
since you figured it out.
Because
Q ultimately
well, it
coincides
says
with
that Q ultimately coincides with P.
Which means what? It's moving, Q is all moving where?
Q is moving toward the fixed point,
Towards the fixed point, what is it?
P.
P.
And as Newton says that a continuous curve means like there's only one tangent at every point.
Okay, well,
And then
well, how do
the
you,
other way
again,
is
the
that-
question is how do you know that this critter is a tangent?
And so like
Because it no
that every point has only one tangent, and since Q is coincides with P, therefore it's not Q is not a secant. No longer a secant cutting the curve.
I'm not convinced. What, the question is why must what? Why must PS be a tangent? Why must PS be a tangent? That's my question for you. That's the heart of the proof. The heart of the argument is that PS, under the conditions of this lemma, PS must be a tangent. Why is that true? It's in the text. Make sure you understand it.
Okay.
It's not because
It's not because there's a okay, what you're saying, once you know that PS is a tangent, then you've got a problem, because now you've got more than one tangent at every point. But you only have the problem if you can prove that that's a tangent. Do we understand?
oh
You understand the issue?
yeah.
You have a problem once you've proven that it's a tangent. But if you can't prove that it's a tangent, then you don't have any problems. The reductor doesn't work. What do you got? Keep working at it.
So what is a tangent? It seems like
Yeah, Dave.
So
tangent is equal. It's a straight line that meets
it no longer cuts the
at a point, right? At a point
No
of
longer
another
cuts
shape.
cuts the
Oh, yes.
But
And
as B
we're worried
says
about
Q
PS.
approaches to P,
Okay,
there's
let's make
only
sure-
one point, and as P only
make
goes
sure you
to
understand
P,
the sense.
therefore it's a
Start with this,
Right.
read to
Because it only
the,
touches at one point.
from sense to therefore.
But since there
Make
is
sure you
PT,
understand.
Yeah.
another
It's not
tangent
changing.
can't be happening.
Good, let's make sure that you know, see the sense here? Sense Q?
another point.
Yeah.
Make sure you understand the sentence. Sense Q ultimately coincides, right?
PS to prove that.
What page?
Okay.
Make sure you understand that sentence. See it? Sense what?
Since Q ultimately coincides with P.
Do you understand that sentence?
Mm,
Do you? If you do, then you'll understand why that must be a tangent.
Since Q ultimately coincides with P, PS must fall in the space between the tangent PT and the curve PR.
Why?
Why? Is not straight line.
Why is that statement true?
No.
Because you line
I
over
think the keyword is ultimately.
Clear it up, clear it up.
Therefore, that's a tangent.
Remember, SPT is the angle approach
Kind of like
by what?
Before we went on vacation,
VPT,
we were talking about limits the whole class.
right? But Q is going where?
That's the limit.
To P. That means that as Q diminishes, what is it diminishing to?
Yes.
It's ultimately going to diminish. VPT is going to ultimately diminish to what?
SPT.
Q is going to P.
Right?
Yeah.
As V, where's Q going to go?
V.
It's going to ultimately end up where?
P.
At V. So where must,
Yeah, but
where must
we assume
SP?
that
Put it the other
it's no
way.
longer
If SP
it's
cuts this, say SP was a secant.
Assume it's no longer Assume.
Put it that way.
Assume that.
If SP is a secant,
Angle B,
Could you
P
get all
is
the
not
way to
vanishing. So there
Think
has to
about
be a
that.
line, an angle.
SP is a secant.
What is no line between the tangent BT and the curve
Yeah. Okay, if it got all the way
Then
there,
it doesn't
no
vanish.
longer secant, but
The angle
Remember,
fits
angle
VPT
is
tangent, right?
diminishing.
Yes, prove that PS
And we're assuming that it's going to diminish to what
we
angle?
assume that VPT does not approach.
Now, if SPT is not a tangent, it's going to be a what? A secant, right? It's
Yeah.
going to have to cut somewhere,
So yeah.
which would mean that Q would
Yeah,
have,
so
on its
prove
way
that
to
PS
P,
is
Q would have to
Yeah,
do
right
what?
here,
Pass beyond
PQR.
SPT.
What is tangent?
VPT, which has no point
between the tangent VP and QR. And now he's like,
Don't you know that VPT is
Probably a tangent with these say.
approaching SPT. So as Q approaches P, what's going to happen?
Basically possible.
What has to happen?
So SP will be in between the tangent and the
It has to be, right?
yeah.
Now, work it out and convince each other of that. You see what we're getting at here? Okay, if it doesn't go, if SP is not in that space between it, then VQP cannot approach what angle? VPT can't approach what angle?
SPT.
Right? But we're assuming that VPT approaches angle what? SPT. So as Q approaches what? P, SP has to be where? Has to be in the space between the what? So think about it, convince each other of it. Okay? What do you think? Are you convinced? Okay, convince me now.
So secant has to cut it. One
It's not
cut
continuous
curve, but this only.
I know.
It's given a continuous curve. What are you talking about? It's given a continuous curve.
Touches the curve.
Well, how do you know you want to touch it?
Yeah, but this is the possible
Yeah.
curve.
Assuming it's impossible, not the given.
Well, what's important here
So
is
this
that
one
you're
is
assuming
possible.
that what angle? What's the angle?
assuming.
What is
Yeah, and then it's for
SPT?
curve PQR is
No. Yeah, just
and you have only one tangent.
Yeah.
Okay, guys, we're gonna have to wrap this up. We want to thank again Mr. Waterbury for our for being our cameraman. We'll continue this discussion next class until we can convince ourselves that the lemma works, and then I'll have one of you guys prove it at the board. But for those of you watching, thank you very much, and we're signing off.